Welcome back to the course on design of power electronic converters. We were discussing gate drivers and we had started with optocoupler based gate drivers. And last lecture I told you about the important specifications that you should be looking for while choosing an optocoupler based gate driver IC. Now continuing with that, one of the terms that or specification that is important for gate drivers is your propagation delay. So, let us see what is propagation delay. So, let us say you have this input voltage, okay, and the reference is the 0 voltage level, which is explicitly shown here, and you have your input voltage which goes from 0 to high, and then so this is shown as ideal, that means instantaneously it is becoming high, but in practice there may be a little delay in that. This may be little rise time may be there and there may be little fall time may be there, but over here it is ignored. So, when you have this driver IC, so you have your input over here and then you have your output over here. So, the output signal, it is usually non-inverting, whatever we are giving here, the similar nature of output is supposed to come on the other side, on the secondary side. So, this is your driver in between. So, what you will be having is your V out, where what you see is that there is a delay first. As it is becoming high, it does not become high immediately, there is a delay, and then after that there is a rise time. Now, how do we measure this rise time? This is generally measured by dividing the signal into three parts. One is 90% of the final level and 50% of the final voltage level and 10% of that final voltage level. Okay, so from 10% to your 90%, whatever time it takes, that is your rise time TR of that signal. And similarly, the time it takes to go from 90% to 10%, that is taken as the fall time TF of that signal. And the delay, the propagation delay is that when this input signal goes high, from that point to the point at which this output signal becomes 50% of the output voltage level. This is your propagation delay. So, this delay is going to be there both on while it is becoming from low to high, as well as when it is going to be coming from high to low. So, this is your propagation delay that is there, okay, and this is there in almost every IC that you are going to use, whether it is a driver IC or some other IC, every circuit that you use has got some kind of a propagation delay. Now, why is it so important to be counted for in your gate driver ICs? So, you may recall about the dead time. I had discussed this before. So, let us say we have one leg of an edge bridge. So, this is your T plus and this is your T minus, and we had discussed that your T plus, let us say this is the signal, it goes from high to low, and as it goes low there is a gap that is given, which is called as the dead time, after which this T minus goes high, and this time is what we call as the dead time. Now, this dead time, how do you choose this dead time? How much it should be? One is of course that the time it takes for these IGBTs to turn off. And why turn off, why not turn on? Because this also we had seen before, turn offs are usually higher than your turn on times, and they play more important role in the transitions in the circuit. And so turn off time is what you should be checking for. So turn off time of devices. And the second important thing that you should be looking for while deciding your dead time is the propagation delay of the driver. And why is it important? Because you have this driver and then you have the gate resistor, and then this gate pulse goes to the IGBT. Here is you have the PWM pulse that is coming out. So, it actually passes through the driver. So, although your turn off times may be smaller, let us say, then if you have chosen a driver where propagation delay is very high and you have decided your dead time based on your turn off times of the devices, so that dead time will not be suitable, it will not work, it will create problems, because turn off may be happening faster, but the signal, the gate pulse will not reach till the driver operates, okay, until the driver is able to transfer that signal to the output. So, that is why your propagation delay of the driver is what you should be looking into before you decide your dead time for your circuit. Next important specification is the capacitive coupling. So, between your input and output, usually there is a parasitic capacitance. Now, this capacitance between your input and output, what happens is that it provides a path for the flow of current. Now, here on this side we may be giving a signal which is, let us say, from 0 to 5 volt, and on the other side, depending on these optocoupler based drivers, it may be connected to your whatever supply, it may be VG, and this other terminal may be connected to your emitter or the source of the IGBT or MOSFET, and these levels are different. What is the voltage level here as compared to what is the voltage level over here. So, this is different, and moreover these are changing. So, as this transition takes place, suppose it is going from high to low, voltage is changing, here also it is changing, and you have a capacitor in between. So, there is C dV by dt, and so that is the current, and that current is going to be flowing through this. Okay, this is your I coupling, you can say, that is going to flow, and this current is undesirable because first of all it is going to reduce the isolation level, and second it leads to interference issues, electromagnetic interference problems, and also reduces what is called as the common mode transient immunity. Okay, it is a source of noise and it is a problematic thing, and so we should have the capacitive coupling as small as possible. All right. Now, how do people reduce it? Your optocoupler based drivers, they usually provide a shield. It is called as a Faraday shield. With that, to some extent this capacitive coupling is reduced, although we cannot eliminate it 100%, but it is reduced. And so, your this capacitive coupling, as I told you, it is the main source of noise, and this is called as what is called as the common mode noise. Now, what is common mode and differential mode? Those things we will see on later on in the course, and this leads to lower what is called as the CMTI, which we will be just discussing now, and it leads to perturbation in LED current. During common mode transients. Now this perturbation in LED current is what, if this LED current is getting perturbed, so that will, what will happen is that you will see some kind of abrupt functioning. Sometimes the driver all of a sudden it will shut down, and then again it will start up. Okay, so this kind of mysterious phenomena that you may be observing while doing the experiment, and you may wonder that why it is happening. You did everything right, your PWM pulses are correct, your driver circuit is as designed as it should be, but still you are seeing problem. So all of a sudden random effects, suddenly shutting down, suddenly turning on. So that is because of this capacitive coupling and this perturbation in LED current. So that is why this capacitive coupling should be as low as possible. And so related to that is the next important specification of your gate drivers, which is your CMTI. Now this is called as the common mode transient immunity. Okay, so let us understand what is common mode transient immunity. For that, I have taken this example of edge bridge and then one leg of that. So you have got these two transistors, okay, and then they are driven by this gate drivers. So here we have got this reference 1, which is your emitter 1 reference. Then there is reference 2, which is your emitter 2 reference, which is basically the N bus or the negative bus of the DC bus. Further over here on this input side we have the controller, and this controller is going to give you VPWM1 and VPWM2, and these are with respect to this common reference, which is ground 1 for all 3 of them. So this part of the circuit, as you can see, that has got the same ground, whereas over here we have different grounds. Now what will happen is that you have your this capacitive coupling. So let us draw this. That is your capacitive coupling between your these two, okay, input side and output side. And this can also have currents if these voltages are going to change and the levels are different, okay, because C dV by dt is the current, okay. So let us look into the waveforms for that. So first of all, this is your VG1 E1 is the gate pulse for the upper transistor. This is the gate pulse for the upper transistor. Whenever this is on, then this is off. Whenever this is on, then this is off. Now there will be some time between your this lower transistor turning off and the upper transistor turning on, okay. So that, and then over here we also have the dead time. So this is our dead time, okay, and then there it takes some time for it to come down, and it takes some time for it to reach to that upper level. So whenever this is turning off and this is turning on, at that time what happens is that, so this is on, the voltage goes from minus VDC to plus VDC over here. When this device was conducting, this point's potential, A point's potential with respect to N was minus VDC or 0, you can say that, because this is the potential VDC minus, and then you have this when this upper device turns on, the potential over here this gets connected to this bus, so it becomes VDC plus. So that is what we see here. After this upper transistor has turned on, this starts to increase, and then we have a certain rise time, because it is not going to turn on instantaneously, it will not reach that, it will take some time, and it reaches to this VDC plus. So this is your VAN voltage waveform, how it will be appearing. It will be more or less following this VG1 E1. And there will be certain rise time for the voltage to go from VDC minus to VDC plus, and when it is coming down, for it to come from VDC plus to VDC minus. Okay. So this time is, we are calling it as the rise time and the fall time between these two. Now in between that, what we should observe here is that this E1 potential, that means this A potential over here is changing, and this is fixed. So this potential, if it is changing as your waveform was changing, so that will lead to certain levels of currents. So this was your, let us say, COUP, with it will be associated your current, let us call it as the ICM current, okay, common mode current, that will be there, and that is that current which is plotted over here, and it will be there only for the short time period of rise time TR and this fall time TF. This is basically your CdV by dt current that flows through that coupling capacitor. Okay. So every transition in your A points voltage, that means your emitter E1's point, whenever this transition is happening, there will be this common mode current, ICM current, that will be flowing. So this current then comes to this, when it is going to flow in between the output and the input of this high side driver. So it enters into this circuit also, okay. So that is where it creates the interference, it is connected to the ground. So that means now it has entered this part of the circuit, and so it's going to be a problematic thing. And not only that, this ICM, as I told you, this will become also start disrupting the LED that may be there, okay, and it is going to disrupting the functioning of this gate driver, okay. For this lower side driver, over here the current will not be there, because this N is fixed, this is not changing, okay, and this is also fixed. So here this current will not be there, but whatever is current is generated by this high side driver, that itself is going to come here as well, and this it can also disrupt the functioning of this lower side driver. So now the driver should be such that it should be immune to this effect, this common mode effect, and that is what is your common mode transient immunity. And the way we define it as common mode transient immunity as the maximum tolerable rate of rise or fall of common mode voltage applied between two isolated circuits. And the way it is measured, or you can say that it is denoted by your this in terms of your kV per microsecond. So what it is that your this ICM current, this is your C coupling, dVCM, this common mode voltage by dt. This is what it is, say, and so this part of it, this dVcm by dt, whatever it can withstand, that is specified as the CMTI. Okay. Now, for this case, what we had taken, let us say your this VDC, your VDC plus with respect to your VDC minus, let us say that was your 1000 volt, and your TR let us say was your 100 nanoseconds, TR or TF was is equal to your 100 nanoseconds, if that is what it was. Then your this dVcm by dt, this common mode voltage, and note that this common mode voltage only is for this this part, because this is what then this rise times and fall times is what is creating the problem, and it becomes common to both the input and output side. So, here this will then become equal to your VDC plus by your TR. So, that is going to be equal to your 1000 by 100 nanoseconds. Okay. So, then usually this is expressed in terms of your kilovolt per microsecond, okay, or kilovolt per nanosecond is the way your CMTI levels are given in the data sheet, and it should be as high as possible for the better operation of the driver. Now, let us look into the data sheet of an optocoupler based gate driver. So, I have chosen to show you this Fairchild Semiconductors, this driver FOD3180. This is an optocoupler based gate driver, as you can see it is written. And what is the peak output current? It is your 2 ampere is the minimum peak output current. So, I had told you that output current is the specification that you should be seeing. So, gate current it can provide is maximum up to your 2 ampere. So, whatever IGBT or MOSFET that you will be choosing, it should be sufficient, 2 ampere should be sufficient to drive that. That is what you should check in your calculations. Then next important thing is propagation delay. You can see here this is given 200 nanoseconds propagation delay. Then 250 kilohertz maximum switching speed. So, you can use a switching frequency less than 250 kilohertz if you want to use this gate driver. Then further other important is your VCC operating range 10 to 20 volts, which is a wide enough range for your MOSFETs and IGBTs. Then your isolation level is given as 5 kV. Okay, so this is also important. Then other important thing is your common mode rejection or your CMTI, which is given as 15 kilovolt per microsecond. Okay. Then let us see further. So, applications will also be provided. So, this is the block diagram of this IC. It shows that this uses optocoupler, then it further uses some totem pole arrangement as well. Okay, and in different packages it is available. Further other maximum ratings are also given in tabular form. You can go through all of them. Most of it is self explanatory, and the important ones for you to look, one is your VCCV supply voltage, that has to be below 25 volt, and your output voltage is from 0 to VCC, that means whatever is the supply voltage that you apply, maximum that much output you can obtain. And output power dissipation, this is given as 250 milliwatt. So, this 250 milliwatt is the loss that is going to happen. So, based on it you can see how much power loss or cooling requirement. Usually this do not require any other further cooling. Then next your this one, this power supply voltage levels recommended is 10 to 20 volts. Then input current is in milliamperes, and this is very important, as I told you, it should not load the your controller. So, this is the input current which is low enough. Then the input voltage, what your controller I mean off state, it is from 0.8 to -3 volt. So, what it means is that when you have this kind of a pulse coming up, so this can be the low one will be detected if it is between -3 volt to 0.8 volt. Okay, because whatever controller you are using, accordingly you can see whether the low what will be considered as low by the driver, the way it is designed. Then apart from that, many other specifications will be given: high level of output current, low level of output current and voltages. So, there are all these are mostly self explanatory, or if you do not understand it, you should be able to get application notes from the manufacturer, where you the terms meanings are given. Okay, and you should be reading all of these data sheets on your own by now. Okay, and important ones is your this capacitance. Here this input capacitance is given. Okay, it is 60 picofarad. Then for isolation characteristics, your this input to output, which is your basically your coupling capacitor, which is given as 1 picofarad. Okay, isolation voltage level, this we had already seen, it is 1000 volt RMS, and resistance input to output is also provided in the isolation characteristics. And further your common mode transient immunity, okay, this is given as 15 kV per microsecond. Okay, this also we had seen before in the important specification in the first page of the data sheet. So, those are further your given in more detail. So, there may be several other this kind of specifications that will be given in this optocoupler based gate driver IC's data sheet, and you can go through them, and you can read for yourself that what are the important things that you should be looking for. So, what are the key points of this lecture? So, propagation delay, we discussed that is something important in the gate driver to note down. Then next is your isolation level, your optocoupler based, if it is optical isolation levels, you should be checking for, and associated with that is your capacitive coupling. That also you should be checking that it should not be too high, and with the capacitive coupling is also associated is your CMTI, common mode transient immunity. This level should be as high as possible, and this denotes how much your driver is going to be sensitive to noise or the different transients, transitions that are going to happen in your power electronic circuit. Thank you.